What is the difference between forward and reverse bias in electronics? Imagine flipping a switch that either allows or blocks electrical current from flowing through a device. That's essentially what forward and reverse bias do in electronics. They are two ways of applying voltage across a diode, and they change how the diode behaves in a circuit. Understanding these differences is key when working with semiconductor devices like diodes and transistors in analog electronics and embedded systems. In forward bias, you connect the positive terminal of a voltage source to the p-type material, which is the anode, and the negative terminal to the n-type material, the cathode. This setup creates a voltage that opposes the internal potential barrier of the p-n junction. When this barrier is weakened enough, charge carriers like electrons and holes can cross the junction easily. As the voltage increases beyond a certain point, called the threshold voltage, current flows freely through the diode. For silicon diodes, this threshold is about 0.7 volts, and for germanium diodes, it's around 0.3 volts. In this state, the diode acts like a conductor, with low resistance, allowing a large current to pass. The current increases exponentially with the voltage, making it useful for converting alternating current to direct current in rectifier circuits, or powering light-emitting diodes that emit light when current flows in forward bias. Now, reverse bias is quite different. Here, you flip the connections. The positive terminal connects to the n-type material and the negative to the p-type. This setup causes the external electric field to reinforce the internal potential barrier. As a result, charge carriers are pulled away from the junction, making the depletion layer, the region around the junction where charge carriers are depleted, widen significantly. This widening increases the diode's resistance, and almost no current flows through it. The diode acts like an insulator blocking current. However, if the reverse voltage becomes very high, reaching what's called the reverse breakdown voltage, the electric field becomes strong enough to ionize atoms in the depletion region. This process causes avalanche breakdown, allowing a large current to suddenly flow in the reverse direction. This is used intentionally in devices like Zener diodes for voltage regulation. The main difference between forward and reverse bias lies in the polarity of the applied voltage and how it affects the diode's internal structure. Forward bias reduces the potential barrier and narrows the depletion layer, letting current flow easily. Reverse bias increases the barrier and widens the depletion layer, blocking current. This physical change in the depletion layer directly impacts how the diode conducts or insulates. In practical applications, forward bias diodes are used in rectification, LED lighting, and voltage clamping. Reverse bias diodes, especially Zener diodes, are used for voltage regulation and circuit protection. The ability of diodes to switch between these states quickly and efficiently makes them essential in both analog and digital electronics, controlling current flow, protecting circuits, and enabling switching functions. So next time you see a diode in a circuit, remember that its behavior depends entirely on whether it's in forward or reverse bias. And that difference is what makes diodes such versatile components in electronics.